So today is September 8th, 2011, AP Calculus at Berkeley High School. And we're going to pick up this lecture where we left off. One of the real typical things that we have to do to show that we understand the definition of derivative and not simply just the shortcuts that allow us to find the value of the derivative function is given a graph, what is the graph of its derivative? And I think we started yesterday and we started saying, well, you know, when we're at 0, we have a slope of 4. When we were at 1, it looks like we had a slope of about 1. And I continue to try to tie in an idea that the derivative function returns the slope of the tangent line. So here we are at 1, and it has a slope of about 1. And now here we are at 2, and what about the slope of that tangent line? Perfectly horizontal. So that's when x is 2, the slope is 0. Now we go on to 3. And again, I'll draw that tangent line slope. And now we see that the slope is decreasing. As we go further to the right, the y values decrease. So now at 3, we're looking at a slope of -1. What happens when we get to 4?
Still -1.
Still -1?
Yep.
This looks almost linear along this expression, along that line? No, okay. So let's say that that is indeed -1 there. And same for E, which is at 2, 3, at 5, down here. And now what happens at 6? 0. And then what happens at 7? That tangent line looks 1-ish?
Yeah.
Okay, so here we are at 7, and now we're going back up to 1. So we could say that this is the graph of f prime. Here's the graph of f, and here's a graph derived from f, the derivation of f. Good?
Good.
All right. Your turn. Let's do something fun. Here's a curve. I'll call it f of x. Copy it into your notes. Work with your partners. Would you please show me what the curve f prime looks like?
Okay. All right. You should write it before I do, because you have a pencil.
Okay. What do you think the slope at 0 is?
My son is going to be that true.
0? It's not really going down. I think it's like the hill at the top of a curve.
He's a big fan of the Lego Star Wars.
It kind of goes down. I guess that's 1.
He's looking forward to the Harry Potter, Lego Harry Potter coming out this fall.
Sure. I mean, if you just drew a thing, I kind of think that's just like the top of a hill.
Okay. We'll go with that. And then
Like, do we pick at points? Yeah.
Sure. I'll just call this A. I'll call this B. I'll call this B is with a B. And I'll call this B. How's that sound?
So at A, B, C. Okay.
And you know what? I'll call this point
Negative A.
no 1. I'll call this -1.
Okay. Oh.
So what do you think about that? What do you think that the graph of f prime is going to end up looking like?
okay, well,
Here you go.
check.
Did you check it over with your partner? Okay. So you guys are in agreement? All right. So watch all the chords.
Yeah.
At A, I think it will be -1. At B, it will be 0. At C, it will be +1. And then D is 0.
Okay.
So let's just wait for him to try.
So not only are you going to write your answer up there, but you're going to discuss it, and people are going to say, yes, I agree with you, no, I disagree with you, or I have no idea what you're doing.
We disagree just because we feel like it. Nope.
Yeah, I figured someone would.
Good description of what you did. Thanks for.
Sarah, you have something to say? Is it an agree, a disagree, or I have no idea?
Back.
Okay,
It goes down first. Slope at first is negative. You have to go down first, then up.
thanks, Rick.
No, leave it up. Leave it up. We gotta disagree with it.
No, you don't get to disagree with them.
Oh.
Okay, Sarah,
Uh,
tell me about your disagreement.
Not a research.
what he did is,
Wait, leave it up there for a second.
um,
Leave it up, okay.
There you go, it's back.
I think that he did the inverse of what the derivative is, because as you go down the first curve of it between the origin and A, it's a negative slope, so it would be an inverse of that.
Okay. So your problem isn't, we're going to accentuate the positive here. Your problem isn't this point right, sorry,
Back, right.
that point right there, is it?
That's
You agree that at 0, the slope is 0.
Mhm.
Okay. Your point is that along here, slope is negative. The function is decreasing, so the slope is negative. But you
Accidentally mirror imaged it.
mirror imaged it, had a reflection of it. Okay, so go ahead. Let me put this back. You go ahead, erase, and make changes. And let's see if we can get something that looks right.
There you
6
go,
years
Matt
ago,
Grant.
I taught my first Calculus 3 class here at Berkeley High. And the class was very small. Had only 5 students.
You got a class
All
with
guys.
Only 5 people.
Hold on. And it was the year that Borat came out.
Oh,
So the number of times I heard, very nice. Oh, okay. All right. So there's my warning. No more Borat. All right. So, does that look appropriate now? Sarah, are you happy that this is negative, or this is negative while the function is decreasing here?
Yes.
And the function continues to decrease all the way to b, and it stayed negative all the way through b. Yeah?
I'm happy with that.
You happy with that? I'm happy. Full credit.
Matt Grant is a boss.
All right. Now, we're going to flip it. Then we're going to bop it. Then we're going to twist it. No, we're not going to do that. I'm going to change the question. Here's the graph of f prime. Here's the graph of f prime. And here are some other things I want you to incorporate in your graph. F of 0 is equal to 0. The graph of f prime is the derivative of f. And f is continuous for all x. Can you please draw for me what f looks like, given that I've just given you the derivative function? Okay, work on it with your partners. Go. So remember, I'm giving you f prime.
Should we draw the beginning?
Giving you f prime. You need to give me f.
Slope is 2 from 1.
So, I guess if we don't look at the book, then we can say that.
What?
First of all, I think we should list that f of 0 it crosses the origin. It's given, so we might as well leave it here.
That's tragic.
No.
And then
Being sent to Iraq and dying.
negative
Supervised.
So-
That's tragic. This is simply an opportunity to
It
live.
passes through the origin.
Yes. 1.
Alright, so we got a point.
2, so then I know it's -1.
So there isn't a slope at 1, though.
Then after point
And the
1,
slope is undefined and a line is.
-1 directly
And then everything before 1, the slope is -1.
Do like a checkpoint point thing? Yes.
So it's going down.
Make sure that your partner is all the way with you.
No.
You got it?
Yep.
Absolutely.
You got it?
Or the slope is 2 on the right side.
Okay.
And then at 1 it has
negative straight. Or
I think you are not
So it's like
slope
using
to the
item
right.
number 1.
it goes like -1.
Oh. It's got to go
That?
through.
I just tried to tell him.
Well,
Well, it has to be
okay,
straight
can
up
someone-
with
Can someone
1.
please
What?
tell me, what does it mean that f of 0 equals 0?
What does that say?
There's a
plug
point
in.
at the
In
origin.
in the original function, there's a point.
This
In the original function, there's a point in the origin. It's got to go through the origin. So,
Because
and it's got to be continuous, so it's not because you're going to put a point in the origin
there
and
isn't
the rest
a
of it
slope.
avoids it. The line's got to go through that point. So check your answer and say, do you have that particular attribute?
Yeah, I was thinking of
The only time you don't have slope is
Mr. Demery, go ahead and draw your answer.
That's get it. Well, when you're
I know it made me mess up earlier.
let's see what Jimmy bites.
Gonna send you to mathematician jail, divided by 0. Okay, so between all your partnerships, have you got something that you think is correct? Yeah? Okay, does it match Mr. Demery's?
What up is your stuff?
I disagree because that was
I'll take care of it, I'll take care of it.
because the
Only calling what I
derivative
was
shows
saying.
that -1 is the slope on the left side. It's not 2 or -2.
Okay,
It's shown as
so let me see if I can understand your complaint, Mr. Demery.
Yeah.
Mr. Raisky believes that this slope is not -1.
No, it is
Oh.
-1. That looks like -2.
I think.
Oh wait, the slope over here is supposed to be -1, but this is drawn like it's a -2 slope.
Oh. What?
Is that a statement of your problem with this? Mr. Demery, reply?
He's right.
Okay,
You got beef, though? You trying to call me out?
so if it had a -1 slope, it would go through the point 1, 1? Sorry, 1, -1?
1 -1.
So it'd be more like that, a little bit flatter than
Yes.
this one, and then we're gonna have to have a positive 2 slope coming out of here. So it's gonna go over 1 up 2. So it's kind of going like this. Is that closer to what you're thinking it's gonna be?
Yes.
Okay. Are we good there? What's going on here?
Are we missing
There's a.
there should be a hole in 1 negative.
No.
Should there be a hole?
No.
I'm looking at item number 3, and it says f is continuous.
Oh.
So if we had a hole, could it be continuous?
No.
No, Sarah.
Wrong. You
No,
wrong.
it doesn't need a hole because in the derivative, because there is no, because the limit does not exist, the derivative does not need to be continuous.
Okay, so the derivative is not continuous. That's true. And the manifestation of that lack of continuity in the derivative is not a lack of continuity in the function, but rather this thing. You know what I'm going to call this thing? I'm going to call it a corner.
Oh.
I'm going to call it a corner. All right? And what we find is when we have a lack of continuity in the derivative, we end up getting things like corners and cusps.
Vertical tangents.
And possibly vertical tangent, yeah. All right? All right. That was an interesting problem. All right. Any questions before I go on to the next slide? We're good? All right. All right. Let me explain what this slide is. There's something called the birthday problem. Has anyone ever encountered the birthday problem before?
Yes. Yes.
Okay, Zoe, can you give me the description of the birthday problem?
Well, I don't know about the problem, but
So.
Oh, no.
wait. Okay, what exactly am I supposed to explain?
Well, I mean, there are certain ideas in mathematics. There are certain ideas in mathematics that have their own name.
Like the more people there are in a room, the more probability that they'll share a birthday.
That at least one pair of people share a birthday.
Okay.
Okay? If you have 5 people in a room, there's a 2.7% chance that 2 people share a birthday. 2 of the 5. If you have 10 people in the room, there's 11% chance, almost a 12% chance, that 2 of the 10 people will share a birthday. Sorry, at least 2 of the 10 will share a birthday. And when you get up to 25, there's almost a 57% chance that at least 2 people share a birthday. Now, what do we have in here? 14?
Yeah.
So they say that there's a 25% chance that 2 of you share a birthday. 1 in 4.
August 24th.
Wait,
February
sorry.
16th.
Okay, sorry. Organize. Any Januaries? I'm in January, so I'm all by myself. February. No other Februaries. March.
18, 27.
Okay. April. May. 15th.
19th.
Okay. What's after May?
June.
June. Sorry, what's after April? June. All by yourself. July. All by yourself. August.
What up?
September.
22nd.
Ooh. What's after that? Where were we?
October.
October.
What?
21st.
You have a twin.
He has a twin, so you could just get him in the same room.
And you have a twin, right?
Just bring him in.
So I got 2 halves of twins. Okay, November, December. So close.
Have you ever
Okay.
actually had 2 people in your room share the same birthday?
Oh, absolutely, absolutely. Especially when I have twins. Like I had, which pair of twins I had last year in stats? Lisa and Scott Tensor. And they were in both of them class in the same day, or in the same class, and they had the same birthday. But actually, and it's just like, 1 in 25. That's still not great odds, but it's really surprising that once you get higher, these probabilities get really, really large. Who would have thought that we get up to 50, you have a 97% chance that there's going to be a pair of people with the same birthday. It's a really anti-intuitive outcome for this particular problem. But that's not the reason why I'm bringing the problem up. Okay? The reason I bring this problem up is because I want to look at this in terms of slopes. I want to say that this is x and this is f of x. Right? I would like to please know, is there a way to estimate f prime of x given this data? Yeah.
For if you wanted to find on f prime of x the point 2.5 f prime of x, you could do, for the 2.5 you do 5 minus 0.
Okay, hold on. I want to stop right there. Because you chose 2.5. I didn't. Excellent choice. Excellent choice. Why? Why is it a good choice? No. You know why it's a good choice. I want you to try to climb into his mind for a second. Why is that a good choice?
I have turrets and machine guns in there.
Let's see. You called him a bad name. Now you're talking about having...
Hey, that's a death threat. That's suspension.
Sarah, why do you think that's a good choice? Because I think it's an excellent choice.
Because at least I think that what you're doing is you're giving a point in between the first two so that you can calculate the slope in between the 2 points.
That's exactly correct. We're not given complete data. We're not given complete data. Nor do we want to even fathom what does it mean to have 2.5 people in your classroom.
You can have 2.5 men.
But a good way of thinking about the estimate of the value of f prime at 2.5 would be to say, oh, it's the
Midpoint.
well, it's the slope of the point either side. I don't want to use the word average. What I really want to say, what it is the secant. It's a secant line. Using a secant line to estimate the value of a tangent line. And I might write it down this way, that this slope is approximately f of 5 minus f of 0 divided by 5 minus 0.
Y2
y2 minus y1 over x2 over minus x1. Okay? 2.5 is a reasonable place to do that because you're smack in between two known points. And indeed, we could go through and not only estimate that value, what other values might be a good, what value of x might we make a reasonable estimate of the value of the slope?
7.5.
It's 7.5?
12.5.
Because it's,
It's halfway between.
okay, and you would use this one,
or
F of
f of 10.
f of 10 minus
F of 5.
f of 5 divided by
10 minus
10 minus 5. Okay, great. Now, that being said, I'm going to ask a question. And this is not going to be as good as answer as this. But if I was really forced into a corner, sorry, I need to make estimation marks there. If I was really forced in the corner and someone says, Mr. Feder, I know it's tough, and I know you can't do it well. Can you please estimate the value of f prime at 30? Got one answer. He thinks, Mr. Pico knows, thinks she knows. Mr. Reyes thinks he knows. Ms. Simon, you with us?
Oh, no, I'm not with you guys.
Can you apply the earlier logic to this new situation?
Yeah.
And I'm already telling you, it's not going to be as good.
I guess I can.
Maybe.
Yeah, how much you coming?
Use 35 and 25.
Does that seem reasonable? F of 35 minus f of what? 25 over 35 minus 25. Yeah, that's a reasonable estimate. Now, it's not as good as finding the estimate at 2.5. Why? Because we're further and further away from the point where we're actually doing the estimate. When do the estimates get really, really great?
When they're tiny.
Closer.
When they're really, really close to the point we're estimating. Well, I was going to say something like when the limit of the distance around that point approaches 0. When h approaches 0. In which case, when h approaches 0, we don't actually get an estimate. We get the real thing, the exact value. But these are reasonable guesses and reasonable ways of finding those. I bring this up again because not everything in calculus is here's a function, find its derivative, and use the shortcut. We have to understand the idea of derivative. Right. Let's talk about a couple other things. They're called one-sided derivatives. Now, we already know from our discussion about limits that we can take a one-sided limit. Take it only from the positive side. Find the limit only from the negative side. Well, when we take our definition of limit when we take our definition of derivative and we apply a one-sided limit, we get a one-sided derivative. Right? Now, why is this important? Well, as we saw before, derivative functions may be discontinuous. There may be locations where there may be locations where the derivative doesn't exist. And one of the places that happens is in this thing called a piecewise defined function. Now, if I drew this function out, what would it look like? Well, when x is less than 0,
It's a parabola.
it's a parabola.
And then it's a
But when x is greater than 0,
line with a slope of 2.
a line with a slope of 2. Right?
Right.
Now, at this location where there's the corner or cusp, and later on, by the way, I will define corner and cusp as two different things, but we can just think of it where the graph makes a sort of a sharp point. All right? We know that the derivative is undefined, but that doesn't mean we can't look at the derivative just before 0. And we would call that derivative the right-handed derivative.
Berkeley High School staff and students, pardon this interruption, but I just need to take a few minutes to go over a few things, just to clarify a few things. First, I want to talk about lunch. Yesterday was our first day at lunch, and the cafeteria was pretty much left a mess.
Okay, I'm going to turn this recording off, and I'm going to give you the assignment, the rest of your assignment.
In the cafeteria, the